So I will give a brief introduction about the spectroscopy. In the paper 7, we have right spectroscopy, right? So first, we'll recall the spectroscopy. So what is mean by spectra? So what is spectroscopy? So here the spectroscopy, right? Spectroscopy means where this EMR, when the EMR is exposed on a particular matter. So here you have the matter, right? So when the EMR, what is EMR generally? Electromagnetic. Hmm. Yeah, radiation. So when you know that EMR, electromagnetic radiation. Electromagnetic radiation is a composition of all the radiations. X-ray, gamma rays. So variety of various radiations are there. Gamma rays, right? Various radiations with different ranges. So then this particular radiation, right, the bunch of radiations exposed on the matter. Here it's matter, it may be chemical substances. In compound, when it is exposed on this one, what happens here? So this matter will be those particular amount of EM. So it absorbs the EM. It is okay. So it is giving the corresponding. For example, if you calculate to or the investment, so it absorbs UV range of the radiation. You cross the visible range of the radiation, it absorbs that particular. Okay, so like that, here the radiations are positive is absorbed that one, and corresponding, right, the signal is obtained by analyzing that signal. Okay, so we will identify the nature of that particular. So generally here, the spectroscopy is just characterization, the main application of this particular spectroscopy. So you can characterize the compound. So characterization purpose is spectroscopy, right? Like qualitative results. qualitative identification purpose, this particular technique. And generally, very advanced technique, right? So, among all the identification techniques, qualitative techniques. So, this is very advanced technique, right? Superior technique. Okay. Like generally, the analysis is two types. Analysis have two types of analysis. What are those? Qualitative and quantitative. What do you mean by qualitative? Yeah, the qualitative means where we check the quality of the compound, right? Quality or the purity of the compound. So this particular spectroscopy comes under qualitative analysis. By using this particular qualitative analysis, means here qualitative analysis it refers with what is present in the particular compound or the substance in that time. So we will go with that, right, to analyze the what is present in them. Okay, for example, if you have carbon, right, make any benzene, this benzene, we go with this qualitative analysis. So we'll go check. So what is present in the benzene? So tell me what are the ingredients? Means what are the elements present in the benzene here? Carbon. This is carbon. Carbon. Carbon and hydrogen. Hydrocarbon. Is it? Aromatic hydrocarbon. And we have four bonds and five bonds. Right? So like that. This is refers to quantitative analysis. And another thing is the quantitative analysis. The quantitative analysis refers to the how much is present. How much is present. So we won't concern with the what is present in that. Right? So we don't go with that what is that the nature of compound or anything. So whatever the compound is there, whatever the matter is there. So what is the quantity of that? What is the weight of that compound? So that thing we consider. Right? Quantity. Quantity. Quantity means the amount. How much amount is present? Whether it is 1 gram, 2 gram, or milligram, micrograms, whatever. That thing we are going to see this. Right? And this particular qualitative knowledge is again two types. Okay. This review.
Good morning, sir.
Yeah, good morning. Right? Yeah. So here the qualitative analysis and quantitative analysis. So in the qualitative analysis, again two types here, right? So what is all generally Yeah. Right. So we'll check the quality by using two methods. Okay. One is research chemical method and physical methods. Right. So chemical methods and physical methods. So what are the chemical methods in the qualitative analysis? What are the physical methods and what are the chemical methods? The physical methods, give some example under this one. The physical and chemical methods. Spectroscope, no? Spectroscope, no. The spectroscope is it physical method or chemical method? Physical method. Chemical method. Give the example for this chemical method.
Some reagents can be used. Some reagents can be
What is that? That method called? Some reagents, we are using some reagents, right? Okay. Then what it costs? What you are done in the right? Right. So here, functional group identification. Okay, functional group identification. So it comes under this particular chemical method. And physical method is a spectroscope, right? Spectroscopy. It is a physical method, okay? And means generally when you compare these two techniques, like physical technique and chemical technique, where the physical technique is superior than the, that means the spectroscopy is superior than your chemical method. Why? Why so?
Yes.
Accuracy. Right. Right. So generally here, the chemical techniques, that means it is a laboratory technique with the human beings, right? So we'll operate these techniques. Means whatever the reactions or whatever the things, we won't do that. So some human error may be occurred in that technique, right? But the physical techniques where the human involvement is minimized because it is automatic. It is an automated method, right? It is an automated method. So the instrument, generally this analysis done with help of the instruments here. So human errors are minimized. There is no scope for the having the human errors. That's why this is the superior technique. Okay, and in the spectroscopy, you know that it is classified into various types here. Tell me, classification of spectrum. Mm-hmm. UV. Mm. Yes. Mm. UV visible. UV visible spectroscopy. Then mass spectroscopy. Then mass spectroscopy. Gas spectroscopy. Okay. Gas spectroscopy. అంతేనా further. It's so many types, right? X1 NMR, okay, and C30 NMR, right? L15 NMR, F19 NMR, right? F19 NMR. So based on the nuclei, there are other class, right? The NMR is very strict. For example, if the nuclei is a hydrogen, we call it H1 NMR. Generally, we call it EM, proton NMR. And C30 NMR. If the nuclei is a carbon, so you have this C30. And the nuclei is C30. So already you are coming to us in the first already yes. Okay. Then 15 is the one. Right? So here, these are the elements, right? IR spectrum. Then body spectrum. Body also. Right? What is ORD? This is the classification of elements. What is ORD here? Optical rotatory. This question. Right? ORD means optical rotatory dispersion. Right? Optical rotatory dispersion. So with help of this ORD structure, we can identify the configuration and conformation of the count. Very useful method to identify the configuration and conformation. So what is mean by configuration and conformation?
Structure change, sir. Configuration in this functional groups are in the way.
You can right, so identify this configuration configuration with help of this bodies. Okay. These are the types of body spectrum. Spectrum can be like microwave spectra is there. Okay, microwave. Raman spectroscopy is there. So all these are specs are there. So all these are the quantitative technique methods. Right? For the characterization of the compound, we use it. Okay. So and each and every spectra having its own application, right? Own application. For example, if you yeah, UV visible spectra. So what is the application of UV visible spectra? What is the application?
Types of groups present based on observance.
Group spectra, UV visible spectra. చెప్పండి మీరు తెలుసా వాట్ ఈస్ అప్లికేషన్ ఆఫ్ UV spectra? Is it trouble? ఆన్లైన్ మినిట్ UV spectra అప్లికేషన్ చెప్పండి.
సార్ బాండింగ్ బ్రేక్ చేయడానికి యూవీ లైట్ వాడతారు కదా సార్. ఫోటో రెసిస్ట్ మా దాంట్లో అయితే మేము సెమీ కండక్టర్ ఇండస్ట్రీస్ లో మన ఫోటో రెసిస్ట్ ఉంటాయి కదా సార్, వాటిని బ్రేక్ చేయడానికి యూవీ లైట్ వాడతాం సార్. బాండింగ్ బ్రేక్ చేయడానికి యూజ్ చేస్తాం సార్ ఫోటో రెసిస్ట్. ఇక్కడ అప్లికేషన్ లో వాడతాం సార్.
Here, the application of UV visible spectra is, so you can, the main application is you can identify the unsaturation. Generally, right, the UV spectra is active, UV visible spectra is active for unsaturated compounds. For example, we have this is the HL, the LG, right? Or this is some simple alkyl. Here is alkyl. Right? So, for example, I will EHB. Now tell me what are the compounds are unsaturated, what are the compounds are saturated among these four ABC? D. Saturated or unsaturated? Unsaturated. Okay. Then what is mean by unsaturation? sp2, sp3 hybridization is unsaturated. Only sp3 hybridization is saturated. So here these two are saturated. Cyclohexane and butane. Butane. The saturated compounds. So UV inactive. The UV inactive compounds. And these are unsaturated compounds, UV active. Right? So to right, to get the UV spectra, right, the compound must contain at least one unsaturated bond, at least one double bond or the triple bond. Okay. It must contain double bond or triple bond. This the entire structure, the complete structure is right. The complete structure is saturated. Like you take cyclohexane and N-butane. So both are saturated compounds. So both are UV inactive. So the main application of this UV spectra, UV visible spectra is you can identify the unsaturation. And mass spectra. Next type is the mass spectra. So what is the application of mass spectra? What is the use of mass spectra? Functional group. Only functional, only spectras. Mass spectra, the name itself is telling that. The name itself, mass means molecular weight. Okay. So we can identify the molecular weight of it. Right? So it gives information about the molecular weight of the compound. Right? Molecular weight of the compound. Then NMR weight. Molecular weight. For example, here, benzene is there. Okay. Right? So irrespective of the saturated and unsaturated, so the mass spectra gives the molecular weight of all the compounds, right? So there is no condition to have the saturated or the unsaturated or there is no limitation for this compound, right? So any kind of compounds is going to analyze by mass spectrometry, and you can get the molecular weight of particular compound. So you get the molecular information about the molecular weight of the compound, right? And in addition to this, you can get some other information also, like you can get the information about the nitrogen as per the nitrogen rule. Okay, so you will get the information about presence of nitrogens, absence of nitrogens. So what is nitrogen rule? What is nitrogen rule in the mass spectrum? Hmm? Yes. Rule, that rule, nitrogen rule, and some definition is there. As per nitrogen rule, if the molecular weight of the molecular air, okay, molecular weight of the molecular air is okay, odd, odd molecular weight is a odd weight of nitrogen. If the molecular weight is odd, then odd number of nitrogens present. Okay. If the molecular weight of the molecular air is even mass, even mass of the molecule. Odd mass ఉంటే odd number of nitrogens ఉంటాయి. Even mass ఉంటే zero or even number of nitrogen. Zero. Even number. Zero means there is a chance for not having the nitrogen. Nitrogen అక్కడ in case nitrogens ఉంటే even number of nitrogens. Even means 2, 4, 6, 8, 10 in this number. Right? Minimum 2 nitrogens. Even ఉంటే minimum 2 nitrogens. The mass is odd. Odd mass ఉంటే ఖచ్చితంగా ఒక నైట్రోజన్ ఉంటుంది. ఓకే, సో odd mass అంటే అట్లీస్ట్ 1 nitrogen. The nitrogen must be in this number, like 1, 3, 5, 7, like that. That is nitrogen. Okay, so You can identify this means you can get the information about the presence or the absence of nitrogens from the mass spectrum. Then NMR spectrum. What is the use of NMR spectrum? NMR spectrum of the nucleus. You can identify the nature of nucleate types of. And in that H1 NMR, the main right, the major NMR spectra are these two. Remain only N15, F19, okay, yeah, P31 also. Phosphorus. P31. If why we use for the amino acids, okay, for the proteins, to identify the protein sequence, okay, peptides. So peptide chemistry, we use P31, right? Polypeptides also. Okay. Right. So major C31, sorry, C39 F9. C39 is H1 NMR. These are main NMR spectra which are utilized, which are useful to such a determination of the compounds, organic compounds, especially. Right? Tell me what is the use of H1 NMR spectra? What is the application of NMR, H1 NMR spectra? H1 NMR spectra application ఏంటిది? H1 NMR అంటే హైడ్రోజన్ గురించి యూస్ ఇన్ఫర్మేషన్ అబౌట్ protons. Proton. And here, nothing is there. Right? Benzene is there. In the benzene, how many hydrogens are there? The benzene. The benzene, how many hydrogens are there? Yeah. Voila. Benzene. Benzene, any hydrogens are there? Well, benzene. Benzene, that one. The compound we get good. Benzene, any hydrogens are there? 6 or 12? Like the example? 12. So C6H6. What the formula is C6H6. Right? So right? 6 hydrogens ఉన్నాయా 12 hydrogens ఉన్నాయా కన్ఫ్యూజన్ ఉంటే అప్పుడు ఏం చేస్తాం NMR స్పెక్ట్రా రికార్డ్ చేసుకోవచ్చు మనకు అప్పుడు ఇక్కడ 6 hydrogens ఉన్నాయని తెలుస్తుంది రైట్ అంటే it gives information about the number of protons present in the particular compound. The protons ఉంటాయి and the nature of proton, whether it is a primary, that proton is attached to the primary carbon or the secondary carbon, that nature also identified. And C30 spectrum application is C30 spectroscopy. Carbon nuclei. Use information about the carbon nuclei means number of carbons present in the compound and the types of carbons present in the compound, whether it is primary carbon or secondary carbon or tertiary carbon. Right? So that information we will know and the number of carbons present in that compound. So that information is also obtained from the C13 spectrum. Okay. And N15 nitrogen. If any extra elements like right, heteroatoms are present in the compound, so that information obtained from the N15. Right? So by any elemental analysis also you can identify the presence of nitrogens, sulfur and other CHN analysis. CHN analysis. Right? So that is elemental analysis. But that is not accurate thing. NP30 and phosphorus. So these are the NMRs. IR spectrum, what is the use of IR spectroscopy? Functional. Rotational. So rotational vibration means here generally the IR spectra also called as a rotational vibration spectrum. Right? Is called the rotational vibrational spectroscopy, IR spectra, called as a infrared spectrum. Right? Rotational vibration. So what is the range of IR? IR radiation? 4,000 to 400 centimeters. 4,000 to 400 centimeters. 400 centimeters. 624. 25 to 400. 620. Far IR from range 60. So that is this. So rotational vibration is right. So the means this much energy when you apply the IR range of the radiation, sorry, 4,000 to 625, right? Radiation is exposed or applied on the particular matter, right? So this radiation brings the changes in the rotational energy and vibrational energy of the compound. Generally, the compounds, right? The atoms, whatever the atoms present in that particular matter or the compound or the composition here. So they are right. They are doing mix. They are composed with the some internal energy. They are having the internal energy. Internal energy. EI. EI means internal energy. And this internal energy is equivalent to the gravitational, vibrational, right? So the internal energy is equivalent to the means it is equal to all these of energies. Energy, rotational energy, ER means rotational energy, EV means vibrational energy, EE means electronic energy, right? So your UV visual spectrum, right? UV visual spectroscopy, also called as a electronic spectroscopy. It's called the electronic spectroscopy because it brings the changes in the electronic levels of the energy, right? So, for example, here electronic levels means like you have the alpha level, beta levels, right? In the energy levels, downstate energy level, okay, excited state energy level, right? So, atomic force, electron promotions, electron transformations, right? For example, here is a molecule. Right? This okay, like in the electrons, right? In the atom, some electrons are there, right? So this is the ground state. Is ground state electronic level? Ground state energy level, whatever electronic energy level, right? So when you apply the UV radiation, UV visible radiation on this one, then these are the energy levels. Okay. So many energy levels are there. So this first excited energy level, second excited energy level. These are the excited states. These are the ground states. That excited state, it may be first excited state, second or third, fourth, so like that. So when you apply the energy on this particular electron state, so electron gets converted from down state energy level to excited energy level, right? So it may be right E1 or E2, whatever. E0, right? So this is E0, E0, electronic downstate electronic energy level. This is E1, first electronic energy level. This is second energy. So the electron gets promoted to the higher energy level, maybe E1 or E2 or whatever. It gets promoted to the higher energy level. Right? So, for example, if it is promoted to the E2 level, or sometimes with E1 level or E2. So, the promotion of the electron, excited right of the electron is based on the energy absorption of that particular. So, how much energy is absorbed by the that particular electron? So that okay, so the energy absorption by this compound is obtained as a graph. Okay, so in the graph we use graph is the spectrum, UV visible spectrum, right? So that will be means by analyzing that one. So we will get the information about the so how much energy is absorbed by that. And generally here, all the compounds are having their own means the capacity to absorb the energies. For example, you take the alkanes, right? So alkanes, it absorbs a particular amount of energy. If you take the alkenes, so it has some specific range of the radiation. And if you take the aromatic compounds, or if you take the aldehydes or the ketones, carbonyl compounds, esters, so each and every type of compounds having its characteristic absorption maximas or absorption of the radiation. Right? So it has some range. For example, if you take alkanes, right? So it has some range of the radiation. So if you get the graph or the spectra in that range, okay. So actually, here, what is the range of UV visible spectra? UV visible 200 to huh? 200 nanometer to 800 nanometer, right? 200 to 800 nanometer. That is UV visible radiation range. 200 to 400 is for the UV range. 400 to 800 is for the visible range. Right? So here the compounds, all the organic compounds, right? All the organic compounds are have which they will absorb in this range of the radiation. Right? So, for example, if you get a signal or the band, we call the band broadband, you get the broadband in the UV visible spectrum, right? So, for example, here, down the maximum. For example, you get it is at 180, for example, right? Down the line, it is 180, right? So you get this kind of bands in the UV spectrum. You get the bands here, UV visible spectrum. The broad band is optical. And in the IR spectrum, you get a sharp bands signal. Those are all signals. The NMR spectra, SMR spectra, you get the signal. We call whatever the graph is opting, we call that is a signal, right? But the means the appearance of that signal is different types in the different spectrums. In the mass spectra, you get line spectra. Simply you get lines for one single line. Okay. And in the IR spectra, you get the sharp bands, like inverted, like this, sharp bands. So like that, right? Sharp bands you get the IR. And NMR spectra, the splitting pattern, you get the NMR spectra appears like this. This where the IR spectra inverted, multiplets like doublets, singlets, triplets here. If you get only one line, that's called singlet. If you get a two lines sitting here, then it is called doublet. Then three lines like that, singlet. So means that is the complexity, right? It is one signal only, but based on the coupling with the neighbor protons, the adjacent protons, right? Generally here, the NMR, H1 NMR spectra, whatever the reference proton will be couples with the neighborhood protons on either side of that, the selected protons. For example, this side it have one proton, and right side it have one proton, left side one have one proton. Then there are two neighborhood protons. So that proton will be couples with mutually couples with these two protons, right? Then it gives a signal as triplet because this side one and this side one. There are two protons, neighborhood protons, and as for n plus one rule, n is the n equal to the number of neighborhood protons and plus one. So there are three protons. Okay, three signals you will get. It's splitting, right? So like that. So appearance of this. And the C-type spectra again you get two lines, right? And IR, sorry, UV visible, you get a broad band, right? Broad means some range here. Generally 180 to 190, right? 180 times. So like that. So in the UV visible spectra, right? So we want means indicate the absorption maximum and the right? The UV ray which is radiation with single digit, right? So we will mention the range of the radiation 180 to 190, 160 to 170, 200 to 210, 200 to 205. So like that. So we'll mention in that range, right? So for example, one signal it appears in the 7 ppm, it appears in the 10 ppm. So like that. Right? So ఇక్కడ ఏంటంటే మనకు ఆ range అందుకే so that compound it absorbs the UV radiation in a particular range, right? A specific amount కాకుండా ఆ range వరకు absorb చేస్తారు. That's why we are getting the broad peak, right? So the age guidance, మనకి broad peak ఎంత అంటే ఆ range వరకు absorb చేస్తారు. 180 to 180 something. So, for example, you get a signal in the range of 180 to 185 nanometer. Then it indicates the compound may be alkane because alkanes are right absorbs radiation in the range of 180 to 200. Okay, right? So, at last. And for example, when it means you get a signal in the range of right. So 255 or 271. So 279, 285, 285, for example. 279 that signal which is broad peak. You observe a broad peak in the UV spectra, right? 279 to 280 or 283 something. Then it indicates the presence of carbonyl, CO, right? CO. So that CO it may be a part of your aldehyde, it may be a part of your ketone, may be a part of your amide, it may be a part of your carboxylic acid, right? Because CO will be present in aldehyde, ketone, ester, and amides. అన్నిట్లో మనకు CO group ఉంటుంది. Okay, carbonyl chromophore అంటాం, right? So, 270, that absorption radiation is at 279 to 285 something. ఆ range లో ఉంటుంది. Starting from the 279 to 285. Right? అట్లా మనం దాన్ని ఇట్లా అంటే ఒక గ్రూప్స్, right? In case if you observe a compound level 255 nanometer, means a signal is appears at 279 nanometer. Then it sorry 255 nanometer. Then it indicates presence of aromatic nucleus. Aromatic means benzene, right? There may be a benzene ring. 255 దగ్గర మీకు ఒక సిగ్నల్ వచ్చింది నాకు కనిపించింది అంటే అక్కడ బెంజిన్ ఉంది అట్లా అంటే ద ఇండికేషన్ సో బేస్డ్ ఆన్ ది దట్ ద సిగ్నల్ రైట్ పొజిషన్ రైట్ ద సిగ్నల్ పొజిషన్ సో యూ కెన్ హ్యావ్ ద ఐడియా అబౌట్ ది గ్రూప్స్ కంపౌండ్స్ నేచర్ 180 ఆర్ రైట్ బిలో 200 లోపల ఏదైనా వచ్చిందంటే నీకు ఆల్కెన్ సాచురేటెడ్ ఆల్ ఆర్ సాచురేటెడ్ ట్రాన్స్పరెంట్ మనకు ఆల్కెన్స్ అనేది మనకు ఆల్కెన్స్ వోల్ట్ గివ్స్ అ యూవి విజిబుల్ స్పెక్ట్రమ్ అది ట్రాన్స్పరెంట్ ఉంటుంది అంటే అబ్జర్వ్ చేయరు కదా చెప్పిన విధంగా దేర్ మస్ట్ బి అన్సాచురేషన్ సాచురేషన్ ఉంటే అవ్వదు అదేమవుతుందంటే ఇట్ వోంట్ అబ్జర్వ్స్ కాబట్టి మనకి ఏంటంటే కంప్లీట్ ట్రాన్స్పరెంట్ వచ్చేసి అదే మనకు 220 వరకు అట్లా ఉంటే అన్సాచురేటెడ్ ఆల్కిన్స్ లైక్ అరోమాటిక్ అని చెప్తున్నారు అరోమాటిక్ అంటే బెంజిన్ ఏముంటుంది మనకు ఆల్కిన్స్ ఉంటుంది డబుల్ బాండ్స్ అట్లా కార్బన్ అంటే మనకు 279 టు above that 285 to 90 so like that a range of components so atla we will identify that what the compounds and in the UV visible spectroscopy we have some important terminology here. Yeah. So sometimes here compounds so the attachment of some groups on the particular compound. For example, like I told you, benzene. It is a here is a benzene, right? So benzene is there. So generally here benzene, right? The benzene gives a UV visible spectra 255. Generally it gives means three signals generally. మనకు 180 దగ్గర ఒక సిగ్నల్ వస్తుంది అండ్ 304 అండ్ 255 త్రీ బ్యాండ్స్ వస్తుంది మనకు బెంజిన్లో రైట్ త్రీ బ్యాండ్స్ వస్తాయి 180 304 and 250 ఇట్లా త్రీ బ్యాండ్స్ వస్తాయి బట్ 255 ఇస్ ద క్యారెక్టరిస్టిక్ 304 and 304 is called the E1 band right and 255 is called the E2 band okay so అట్లా మనకు క్యారెక్టరిస్టిక్ బ్యాండ్స్ సో 255 దగ్గర మనకు ఒక పీక్ వచ్చిందంటే సో ఇట్ ఇండికేట్స్ ప్రెసెన్స్ ఆఫ్ అరోమాటిక్ బెంజిన్ and the attachment of some groups on that right the attachment of some groups on the right the benzene chromophore right so it leads to increase in the right increase in the absorption max or the radiation UV radiation right so here 255 the benzene is 255 right so it becomes 80 something right so here then you attach a OH group on the benzene right so means it's phenol it becomes phenol so phenol appears at 280 nano right so for example here this value is this is for benzene for example 250 nano right signal is there but we attach a hydroxy group on that benzene then this band shifts towards the right side. That means here we will write yes. You got it. Right? So attachment of a specific group on that engine, it leads to shifting of the bands towards the right side. Right? So that effect or the shift is called the bathychromic shift. Bathychromic shift. Right? That shift towards the right side or shift towards the higher lambda maximum or higher wavelength. It's called the bathychromic shift. The UV is very important terminology. At some groups, attachment of some groups leads to decrease in the right, lambda maximum, absorption maximum. Right? Okay. So this is called ipsophotic. Called ipsophotic. Right? And some groups leads to increase in the intensity of the band. Here, what is happening here? Where it leads to either increasing the lambda maximum or the decreasing. If it is increasing, we call it bathychromic shift. If it is decreasing, we call this ipsophotic. Some groups leads to increase the intensity, means height of the lambda, sorry, height of the peak or the band. Then it is called the hypertrophic shift. And some groups decreasing the height of or the intensity of the band. Then it is called the hypochromic. This is hyperchromic, right? Here. Hypochromic shift. Right? Hypochromic shift. So in this way, it means some shifts in the UV visible spectrum. Okay, time is up. We'll discuss IR spectra in the next class. UV spectra is complete. Okay, so I'm stopping.